This is the second part of the Introduction to Combustion series. Here I am going to talk more about enthalpies. So let's start with mathematical modeling minds. When we talk about enthalpies, the first thing we should understand is the absolute or standard enthalpy. In this equation, H hat represents an intensive property. Absolute temperature of a component I at temperature T is the sum of the enthalpy of formation of I at standard reference state and sensible enthalpy change of I in going from T reference to T. Enthalpy of formation is the enthalpy associated with chemical bonds. This is evaluated at standard temperature and standard pressure. For calculating enthalpies, we usually use the standard temperature as 25 degrees and standard pressure as 1 atm. If an element is at its naturally occurring state at standard temperature and pressure, it is considered to have a 0 HF. For example, in air, we have oxygen and nitrogen molecules at 25 degrees and 1 atm. So at 25 degrees, HF of oxygen and nitrogen are 0. Sensible enthalpy change is associated only with temperatures. Now, with the basic introduction to absolute enthalpy, we can move on to understand the enthalpies associated with combustion. Consider a reactor operating at steady state. Reactant mixture with stoichiometric quantities enter the reactor at standard state conditions. In the reactor, the complete combustion reaction happens and the products exit the reactor at the same standard state conditions. With assumed complete reaction, we have carbon dioxide and water instead of carbon and hydrogen. And heat is generated from the reaction. After the reaction, if the products have to be at the same conditions as reactants, the heat must be removed from the reactor. The amount of heat removed is equal to the difference of absolute enthalpies between products and reactants. The enthalpy of reaction per mass of mixture is given by delta HR equals enthalpy of products minus enthalpy of reactants. The heat of combustion or the heating value per mass of mixture is equal to enthalpy of reaction with the opposite sign. These terms can be expressed using extensive enthalpies as well. Heating value is the heat of combustion. It is defined in two ways. Higher heating value is the heat of combustion assuming that all of the water in the products has condensed to liquid. Lower heating value is the heat of combustion assuming none of the water in the products has condensed to liquid. This diagram is an enthalpy temperature diagram for reactants and products at constant pressure. Enthalpy curve of products lie below the reactants enthalpy curve. It can be observed that higher heating value is the difference between enthalpies of reactants and products with liquid water. Lower heating value is calculated when water is presented as water vapor. Let's consider fuel CXHY is going through a combustion process. The higher heating value is given by heat of combustion between reactants and products. Here I represent higher heating value using extensive enthalpies. Enthalpy of formation of CXHY count for the reactant's enthalpy. Enthalpy of formation of air is 0 at standard conditions, so we can neglect it here. Products enthalpy is given by carbon dioxide and liquid water formation enthalpies. Enthalpy of formation of liquid water is equal to enthalpy of formation of water vapor minus the enthalpy of vaporization. Lower heating value is simply represented by enthalpy of formation of CXHY minus X times enthalpy of formation of carbon dioxide plus Y by 2 times enthalpy of formation of water vapor. You can read these enthalpy values from thermodynamic tables. As I mentioned, in the previous page we calculated extensive enthalpies. But if you want to find the intensive enthalpy values, how are you going to do it? Heating value for a kilomole of CXHY is given by dividing the delta capital HC by number of moles of CXHY. And in this case, it is equal to 1. If you want to find the heating value for a kilogram of CXHY, then you divide the delta simple H hat C by molar weight of CXHY. In the Introduction to Combustion Part 2, we talked about different enthalpies. Until we meet again with another combustion video, thank you for listening.